Hello, and welcome to the Certified Ethical Hacker Study Guide. In this video, we will discuss Chapter 2-3 and 2-4, IP Addressing Part 2 and Binary Numbering System. Please like, subscribe, and hit the notification bell. Now let's zap into the first topic, after this short break. IPv6. Addressing. As a security professional, you should spend some time reviewing the IP Addressing System Internet Protocol version 6, or IPv6. As mentioned, IPv4 wasn't designed with security in mind, and many current network vulnerabilities are caused by this oversight. This section gives you some basics of IPv6, but reading RFC 2.460 is recommended for more details. IPv6 was developed to increase the IP address space and provide additional security. Instead of the 4 bytes used in IPv4, IPv6 uses 16 bytes, or a 128-bit address. So 2 to the 128th power addresses are available, about 2,000 IP addresses for every square foot on the planet. You might think this many IP addresses aren't necessary, but they'll be needed to support the Internet of Things. Many new products, such as toasters, microwaves, refrigerators, and TVs, can be accessible via the Internet and need IP addresses. Here's an example of an IPv6 number: 1111:075A2:01104:3A2A:1113:1113:7777. If it looks odd to you, a review of hexadecimal numbers might refresh your memory. The colons separate each group of 4 hexadecimal numbers. The good news is that being an effective security tester doesn't require being an expert at translating or memorizing these long numbers. As a security tester, you should be aware that all newer operating systems are configured to enable IPv6, but some router filtering devices, firewalls, and intrusion detection systems are not. This makes it possible for hackers to bypass these security systems using IPv6. You can find numerous articles online that discuss the weaknesses with IPv4, IPv6, and the protocols that support them. Cyber attackers spend hours reading these types of articles. Security testers should too. Now let's soar into the next topic, right after this short break. Overview of numbering systems. Your knowledge of numbering systems comes into play as a security professional. The following sections offer a quick review of the binary, octal, and hexadecimal numbering systems. You learned base 10 math in elementary school, although you might not have realized it at the time. When you see the number 3,742, for example, you recognize it as 3,742. By placing each number in a column, as shown in the following lines, you can see that each number has a different value and magnitude. This numbering system uses 10 as its base and goes from right to left, multiplying the base number in each column by an exponent starting from 0. Valid numbers in base 10 are 0 through 9. That is, each column can contain any number from 0 to 9. As you can see, you get 3,742 by multiplying 2 by 1, 4 by 10, 7 by 100, and 3 by 1,000, and then adding all these values. The binary numbering system, on the other hand, uses 2 as its base. Each binary digit, bit, is represented by a 1 or 0. Bits are usually grouped by 8 because a byte contains 8 bits. Computer engineers chose this numbering system because logic chips make binary decisions based on true or false, on or off, and similar conditions. With 8 bits, a programmer can represent 256 different colors for a video card, for example. Therefore, black can be represented by 000000000, white by 111111111, and so on. Another example of using binary numbering can be seen in file permissions for users: R, read, W, write, and X, execute. A 1 represents having the permission, and a 0 removes the permission. Therefore, 111 RDUX means all permissions apply, and 101 RX means the user can read and execute the file but not write to it. Their symbol indicates that the permission isn't granted. Those familiar with Unix will recognize this numbering system. Unix allows using the decimal equivalent of binary numbers. So for the binary 111, you enter the decimal number 7. For the binary 101, you enter the decimal number 5. Confused? You'll be a binary expert in a few minutes, so hang in there. Now let's fall into the next topic, right after this short break. To simplify the concept of binary numbers, think of a room with two light switches, and consider how many different combinations of positions you could use for the switches. For example, both switches could be off, switch 1 could be off, and switch 2 could be on, and so forth. Here's a binary representation of these switch positions. 0, 0 equal sign, off, off, 0, 1 equal sign, off, on, 1, 0 equal sign, on, off, 1, 1 equal sign, on, on. The two switches have 4 possible occurrences, or 2 to the x power. X represents the number of switches, bits, available. For the light switches, x equals 2. Now that you've been introduced to the basic concepts, you can see how bits are used to notate binary numbers. First, however, you must learn and memorize the columns for binary numbers, just as you did for base 10 numbering. 128, 64, 32, 16, 8, 4, 2, 1. From right to left, these numbers represent increasing powers of 2. To convert the binary number to decimal, base 10, add the columns containing 1s. Adding the values in these columns can be tedious, but you can learn some tricks of the trade to help you translate binary to decimal quickly. However, make sure to memorize each binary column before working through the remaining examples in this chapter. Now let's run into the next topic, right after this short break. Psychologists have found that people have difficulty memorizing numbers of 7 digits or more. This difficulty is why phone numbers have only 7 digits, and a dash follows the first 3 numbers. The dash gives your brain a chance to pause before moving on to the next 4 numbers. Likewise, binary numbers are easier to read when they are separated by a space. For example, 11, 11, 10, 10 is easier to read than 1, 1, 1, 1, 1, 0, 1, 0. If you need to convert a binary number written as 1, 1, 1, 1, 1, 0, 1, 0, you should visualize it as 11, 11, 10, 10. In other words, you break the byte into 2 nibbles, sometimes spelled nibbles. A nibble is half a byte, or 4 bits. The 4 bits on the left are called the high-order nibble, and the 4 bits on the right are the low-order nibble. The largest decimal number you can represent with 4 low-order bits is 15. You should memorize these numbers if you can, especially the ones that have convenient memory aids. For example, 1010 is equal to the decimal number 10. Just remember the phrase, "It's 10, silly 10." 1011 is just as easy. Not 10, but 11. You can make up your own tricks, but you can always simply add the columns if you forget. You can also practice converting decimal numbers into binary numbers by using license plate numbers. For example, if a license plate number ends with 742, you should visualize 0111, 0100, 0010. You can eliminate the leading zeros after a few days of practice. When you get comfortable with the low-order nibble and can identify a sequence of 4 bits quickly, you can move to the high-order side. To help you convert numbers correctly, note that all odd numbers have the low-order bit turned on. For example, 1001 can't be an even number, such as 10 or 8, because the low-order bit is turned on. You can also guess that the number is larger than 8 because the 8-column bit is turned on. Similarly, you can identify 0101 as converting to a decimal number lower than 8 because the 8-column isn't turned on, and identify it as an odd number because the low-order bit is on. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. See you on the next one.